Hello everyone, we are now kind of ready to start designing the controllers in the frequency domain. But before taking the next step, I think it's better for you to see how different kind of controllers behave in the frequency domain themselves. As I already mentioned, we will start at first with the proportional controller, which is the simplest one. GC of S will be in the form of GC tilde, and you know that if I draw the body plot for this controller, in terms of the amplitude, we will have a fixed value like this, which will be equal to 20 logarithm of GC tilde, and in terms of the phase, it will be always equal to 0 degrees, as we have a positive number over here. And since for L of j omega we will combine the body plot coming from the GC and the GP, if we introduce this controller into our system, for L of j omega we will have the amplitude plot shifted upwards by this value, 20 logarithm of GC tilde. So the amplitude plot for all frequencies, for the whole range of frequencies for L of j omega will shift upwards if we apply this controller. And the phase plot will remain the same, as the phase coming from GC is already equal to 0. So by applying the GC bar, you can shift the amplitude plot of L of j omega upwards or downwards depending on the value that you have for GC tilde. So this might be useful in some cases when for example you want to increase the crossover frequency. Yeah? If you push the amplitude plot upwards, usually the crossover frequency will increase as well, but at the same time you should keep in mind that this shifting of the amplitude applies to all frequencies. The next controllers that we are going to consider are the first order controllers. In this video, we are going to consider the PD controller, which is an ideal one, and then the lead compensator. So PD and lead will be considered first. In another video, we'll talk about the other first order controllers, which are the PI and the lag compensator. For each one of these, we have the transfer function in this form. So GC of S will be equal to, if I take the generalized gain outside of the controller, we will have it as 1 plus ST. So it's a single zero. If I draw the pose zero map for this, we will have a single zero at minus 1 over t. And we know that this is an ideal controller because it is not realizable. Yeah? And then for this controller, we can obtain the body plot. GC j omega will be equal to 1 plus j omega t, for which the amplitude will be obtained as square root of 1 plus omega squared t squared, and phase could be obtained as inverse tangent of omega times t. You should already know how to draw the body plot for such a system. In terms of the amplitude, initially we will have 0 dB at very low frequencies. The corner frequency will be equal to 1 over t. This is the corner frequency. Asymptotically, we will have this plot with the angle of 20 decibel per decade. This is the asymptotic one. If you want to draw the exact one, it will look like this one. So at omega equal to 1 over 2, you will not have 0 dB, but you will have some value like 3 decibels. In terms of the phase, we have a 0. At the corner frequency, we will have pi over 4. When omega approaches infinity, we'll have pi over 2. And at very low frequencies, we'll have 0 degrees or 0 radian. And therefore, the approximate phase plot for this controller will be like this. So 1 decade before 1 over t, we can say that we have 0. 1 decade afterwards, we can say that we have pi over 2 as the phase. Okay, now you can see how the application of this kind of controller can change the body plot of L of j omega. At low frequencies, at very low frequencies, there will be no change because we have 0 dB and we have 0 degrees in terms of the phase. At higher frequencies, we will inject, or we are injecting pi over 2 as the phase. This might be a good thing to do because we might need to increase the phase margin, and injecting positive phase to the system would be beneficial. But at the same time, you should pay attention that you are adding this plus 20 decibel per decade slope to the amplitude plot as well. So depending on how our system originally is, this might be acceptable or not. But nevertheless, we know that the PD controller is the ideal one. Okay, so practically we will not use this kind of controller. The next first order controller that we are going to consider is the lead compensator. For lead, if I take the generalized gain outside, we will have GC of S as 1 plus S times T over 1 plus S times alpha T. In terms of the location of the pole and 0, for the lead compensator, we know that we will have a 0 which is closer to the origin and then a pole. The 0 will be located at minus 1 over t and the pole will be located at minus 1 over alpha t. And since we know that 0 is closer to the origin, it means that alpha will be smaller than 1. So we have alpha is smaller than 1 in this case, because we have the 0 closer to the origin. Now we can figure out how the body plot for this controller will look like. We can write down the amplitude for GC of j omega. It will be amplitude of 1 plus j omega t over 1 plus j omega alpha t, which will give us square root of 1 plus omega squared t squared over square root of 1 plus omega squared alpha squared t squared. And we can see that for omega approaching 0, we will have amplitude of GCJ omega equal to 1 or 0 dB. And for omega approaching infinity, we will have amplitude of GCJ omega. We can neglect the ones underneath the square roots, and then omega t will appear at the numerator and omega alpha t at the denominator, and as a result we will have 1 over alpha. So at very high frequencies, amplitude will be equal to 1 over alpha. The alpha therefore determines the distance in it between the pole and the zero, and at the same time it determines the amplitude at a very high frequency. In terms of decibel, we will have 20 logarithm of 1 over alpha or minus 20 logarithm of alpha. Again, keep in mind that alpha is smaller than 1. In terms of the phase of GCJ omega will be equal to phase of numerator, which is inverse tangent of omega t, minus phase of denominator, which is inverse tangent of omega alpha t. As omega goes towards 0, phase will be equal to 0. As omega goes towards infinity, phase again will go to 0 degrees. And since here we have a 0 and then a pole, as omega increases, the phase will start to increase, and eventually it will start to decrease and go back to 0. If I draw the body plot for the lead compensator, let's say that here we have the amplitude, and here we have the phase plot. We have the 0 at 1 over t frequency, at 1 over alpha t we'll have the pole, and these are the same frequencies. The amplitude initially starts at 0 dB. The first corner frequency that we have is 1 over t. After that we will have the angle of 20 decibel per decade, and then we will have the pole, after which the slope will become 0 dB per decade, and we will have the constant value. That constant value is indeed minus 20 logarithm of alpha, or 20 logarithm of 1 over alpha. In terms of the phase initially will start at 0 degrees or 0 radians. Eventually it will go to 0 as well. But as we approach 1 over t, the phase will increase. At some point it will reach its maximum value, and then it will start to decrease and go back towards 0. The frequency at which the phase reaches its maximum value is called as omega m. We have 1 over alpha t here, 1 over t here. And the phase itself at the maximum is called as phi m, the maximum phase that we have for this system. And we have relations between the maximum phase and alpha, which I'm going to write over here. First, for omega m, it will be between 1 over t and 1 over alpha t, and we will have it as 1 over t times the square root of alpha. For phi m, we have the relation between sine of phi m and alpha. Sine of phi m is equal to 1 minus alpha over 1 plus alpha. For alpha, we have alpha equal to 1 minus sine of phi m over 1 plus sine of phi m. So these are the relations that you need to know, for the lead compensator. You should also keep in mind that we have the pole of the controller. For the pole, we have s equal to minus 1 over alpha t. We can say that p is equal to that 0 is equal to 1 over t itself, and therefore you have the relation between 0 pole and the alpha. 0 will be equal to alpha times p. So this is also another relation that we should keep in mind for the lead compensator. Another thing that we need to keep in mind is that at the frequency of omega m, the amplitude will be half of the maximum amplitude that we reach. So it will be minus 10 logarithm of alpha. Okay, so these are some details that you need to keep in mind when you want to design a lead compensator indeed. And now let's see how it is going to act on the overall, let's say, overall body plot of the system, yeah, for L of j omega. At low frequencies, you can see that we are injecting 0 dB and 0 degrees. The important factor here is the positive phase that you are going to inject to the system around the frequency of omega m. So you can design the lead compensator such that you inject around phi m phase. So it will be about phi m, which might be 50 degrees, for example, around the frequency of omega m. So you can pick the value for omega m and phi m as the parameters for the controller. Let's say you found out that omega m should be equal to 3 radian per second as an example, and the phi m that you want to inject is 45 degrees. Once you have phi m and omega m, you will be able to find out alpha. And once you have the value for alpha, you already have the value for omega m. You just refer to this equation, and then you will get t equal to 1 over omega m times the square root of alpha. So out of this, you will have the values for alpha and t, and as a result, your controller will be designed. So the important thing here is to pick a proper value for omega m and phi m such that you satisfy the requirements that you are supposed to do, okay? And once you find them, you will be able to find the proper values for alpha and t. In the example, we will see how to do this. One more thing to consider here is that we will try usually to set this omega m as the desired crossover frequency at which we are going to inject this positive phase, and as a result increase the phase margin. But at the same time, you should pay attention that at higher frequencies we will add this minus 20 log alpha into the amplitude, and around the frequency omega m we will add this minus 10 logarithm of alpha into the amplitude plot. And as a result, the crossover frequency will most likely be increased. It will not be at the desired frequency of omega m, but it will be somewhere maybe around here. So as a result, since the crossover frequency will change, this phase will be considered as the positive injected phase at the crossover frequency, not the phi m that we wanted to have. And therefore, when you want to design the controllers, when you have obtained the value for phi m, usually we add some value to phi m. Phi m will be equal to phi m needed plus some safety margin, like something between 6 to 12 degrees, just to make sure that you will have the enough positive phase injected at the crossover frequency that you will have after using the lead compensator. So I hope you have learned how the different first order controllers that we discussed in this video, PD and the lead, how they behave. You have just learned the relations between different parameters of the lead compensator, alpha and t, and the parameters in terms of the body plot, omega m and phi m. In the next video, which is an example of designing a first order controller, we will see how to find out the values which kind of satisfy the requirements. Alright, so I think that's it for this video. Thank you for watching and see you in another video soon.